We're continuing our discussion of the draining water through a circular hole problem. In part A of this problem, we calculated the speed of the water as it emerges from the hole just after the hole is made. And we want to know the ratio of the speed to the efflux speed if the top of the tank is open to the air. So we calculated these speeds separately here. And if you look at the ratio, basically, just to finish it up, we have for the closed tank case, V bottom, and for the open tank case, V bottom prime, we have a ratio 5.07 divided by 3.96, which is V bottom divided by V bottom prime is 1.28. All right. Now in part B of this problem, how much time does it take for all the water to drain from the tank? What is the ratio of this time to the time it takes for the tank to drain if the top of the tank is open to the air? So how long does it take to drain the tank? Now the volume flow rate, remember, is dV dt, d capital V dt, is the top surface speed multiplied by its area, which is conserved. It is the bottom speed multiplied by the bottom area. This is actually what we use to decide that V top is to be neglected in Bernoulli's equation. But that's precisely what we need in order to calculate the time for it to drain. And V top is actually, according to the continuity equation, A bottom divided by A top multiplied by V bottom. Okay, so this is actually the area of the bottom circular hole, which is pi d squared over 4 multiplied with 4 over pi capital D squared. Pi capital D squared over 4 is area of the top multiplied by V bottom. So you can see that the pi's and 4's will cancel, and I find that this is d square divided by capital D square times V bottom. Now also note that the rate with which the water level at the top surface is coming down is actually minus dH dt, the rate of change of the height of the water column. And this is minus because H is decreasing. H is decreasing, and we see that delta H throughout this process is negative. Okay, so this is basically minus dH dt, that's what we substitute for V top, is equal to d square over capital D square multiplied by V bottom. Now when we calculated V bottom, here we neglected V top because the area of the top is much greater than area of the bottom. This is still valid, so we can still use this expression for V bottom for this calculation. So this is 2 delta P over rho plus 2GH square root. So that's what we know for V bottom. Now, if I multiply both sides by minus 1 and capital D square and dt, I see that capital D square dH is equal to minus D square 2 delta P over rho plus 2GH to the power 1/2 dt. All right. So how long does it take to drain the whole tank? So delta t will be then minus the integral. H goes from its original value h to 0, that is when it is completely drained. It is capital D squared over D squared. Then I have 1 over 2 delta P over rho plus 2g. Now I make h a dummy variable, h prime to the power 1/2 dh prime. Okay? And in order to perform this integral, I'm going to let u square equal to 2gh prime plus 2 delta p over rho. So running out of space here. So let's say that. So let u square equals 2gh prime plus 2 delta p over rho. And this implies that 2u du, if I differentiate both sides, is equal to 2g dh prime. Okay, so 2's will cancel. And for dh prime, I will substitute u du over g. So delta t is minus, so copying my result from the previous calculation, capital D square over D square. That remains. For dh prime, I substitute u du over g, so I'm going to have a 1 over g here, 1 over g. Integral between u1 to u2, the u limits. Then I have u du. Remember, dh prime is u du over g, so I have u du. And then I have this expression I called u squared, so to the power 1/2, it becomes u. So u's will cancel, and I will be left with integral of du, which is u. So minus capital D squared over D squared, 1 over g, 2gh prime plus 2 delta p over rho square root, which will be evaluated between h and 0. So we're going from a height h to a height 0. Okay, so this gives us delta t is equal to capital D square over D square, 1 over g. Now, when I evaluate it, so if I operate this minus sign here, this h goes on top and 0 goes at the bottom. So I first evaluate it at h. So this is 2gh plus 2 delta p over rho to the power 1/2 minus, then I evaluate that 0, which is 2 delta p over rho to the power 1/2. Okay, so if I take this into square root 2g parentheses, this gives me capital D square over D square, 1 over g, square root 2g. Now you can see that here I will be left with an h plus delta p over rho g to the power 1/2 minus delta P over rho g to the power 1/2. Okay, so this 2g comes out as square root 2g. So you divide it by 2g here, 2 goes away, you obtain a g, and likewise here. So now I'm left with this square root 2g over g here. So that gives me, as the final answer for delta t, capital D square over d square, square root 2 over g, then I have h plus delta p over rho g to the power 1/2 minus delta p over rho g to the power 1/2. And that's the symbolic answer for delta t, the time it takes to drain all of the water. Now what is it? Let's substitute the numbers here. Delta t is equal to, remember capital D was 2 meters, so this is 4, capital D square. D was 0.02 meters, so it's square at the bottom. Then I have square root 2 over 9.8, 2 over 9.8 square root. Then I have h, which is 0.8 meters, plus 5 times 10 to 3 pascals, that's the gauge pressure, divided by 1000 times 9.8, 9800 to the power 1/2, minus 5 times 10 to 3 divided by 9800 to the power 1/2. And this gives me a delta t of 1.944 10 to 3 seconds as the answer. Now, it was also asking me in part B, what is the ratio of this time to the time it would take if the tank of the top of the tank is open to air. Now, if it is open to air, then I have delta P is equal to 0 pascals. There will be no gauge pressure. And then I would have a new delta T value, which is capital D square over D square. Now you can see I'm substituting delta P equals 0 here, so I obtain square root H. So this will become square root 2H over G, 2H over G, and that's my symbolic answer. And if I substitute the numbers, I obtain delta T prime equals 4 over 0.02 square. Then I have 2 times 0.8 divided by 9.8 square root, which gives me a delta T prime of 4.04 times 10 to 3 seconds. Now remember, the bottom was about a meters per second greater when I had the gauge pressure, and that reflects as in the time it takes to drain the tank as well. So you can see it's about half the time it takes to drain the whole tank if I have the tank closed. So if it is open to air, it takes about twice the time. Now, if I look at the ratio, delta T over delta T prime, delta T is the time it takes with the gauge pressure closed drain. So it is 1944. Delta T prime is 4040 meters per second, which gives me 0.48. So it's about 50%. All right. So in part B of the problem, we were asked to find the time it takes for all of the water to drain from the tank and compare it to the time it would take if the top of the tank is open to air. For that, I looked at the volume flow rate equation because this is a continuous flow. I have V top times A top equals V bottom times A bottom. So I can see that the speed with which the top surface comes down is D square over capital D square times V bottom. And the speed with which it comes down is minus dH dt because delta H is negative. And equating this to V bottom, and since this area of the top surface is still much greater than A bottom, throughout this flow, V top is much less than V bottom. So this equation is still valid for V bottom, the one we obtained in part A. We solve for H by for delta T by integrating this equation from an initial height H to final height 0. And performing this integral, we have obtained this result. And when we substitute for delta P 0, which is the tank open to air condition, we obtain a different result. So these two results basically tell me that when it is maintained under a gauge pressure, it takes a lot less time in order to completely drain the tank.